So I'm counting on you. This might be, yeah, this slide. You guys do have this slide. I'm counting on, this unit's all about looking at atoms. Okay, so we looked at how much an atom weighs. We looked at what we know about an atom, the 3 subatomic particles, and you guys are good about talking about the nucleus. We have protons and neutrons. The protons say what sort of element an atom is. Okay, and the electrons are in a cloud outside the nucleus. So this unit actually focuses on electrons. So the thing about electrons is, if you look historically, okay, we've come a long way with regard to electrons. And you're actually going to see me refer to Bohr, and then finally Schrodinger is the most recent kind of picture of what we know the atom to be. But Bohr actually talked about those little orbs, those little yellow orbs outside the nucleus, outside the look like orange orbs, I guess, outside the kind of the yellow nucleus. Those are electrons according to Bohr. And Bohr said electrons are great. Electrons tend to have different energy levels. Okay, and Bohr actually kind of built on that. Okay. So the Schrodinger built on that. Okay, so the Bohr model, the thing that's wrong with the Bohr model, quite frankly, is it tends to have electrons orbiting because of gravity. You know, like the planets orbit the sun because of gravity? It tends to have electrons orbiting the nucleus because of something kind of like gravity, and that's not how it works. In fact, planets are quite orderly when they orbit our sun or the star or a star. You know, most stars have planets. But when electrons buzz around a nucleus, not quite so orderly. But the thing that Bohr had right was that electrons are not all created equal. An electron that is associated with an atom has different energy levels. So Bohr was right there. Okay. So Schrodinger, actually, and if you, one of my favorite little videos says Schrodinger used lots and lots of mathematics, calculus, etc. So Schrodinger basically came up with a distribution, a probability of where an electron is going to be. Like Bohr, Schrodinger said electrons are not created equal. Electron around a given atom will have different energy levels, so that's cool between Bohr and Schrodinger. But Schrodinger said they don't systematically orbit like the planets. So, okay, so we're going to talk about that cool kind of region of space. And so I think we may have seen this before. Well, I don't really play a game, but... Okay, so electrons are not created equal. Electrons around a given atom are not created equal. In fact, a cool thing it's called the Pauling's exclusion principle. It's clear at the end of this part, one of the last slides. And it says that if you have a bunch of electrons around an atom, which is awesome, it happens, none of those electrons are identical with regard to what we call 4 quantum numbers. They each have to be unique, which is kind of fun. So the energy of electron is going to be what we call quantized. Now I will, for your next unit exam, and I hate to kind of keep harping on the exams, like, come on, it's out there, right? But I will have a vocabulary section. So here in this part, there are definitely some vocabulary words that are kind of nice to throw in there. So we're talking about electrons. And the energy of electrons around an atom are what we say quantized. And all quantized means is that it can be either here, okay, where I draw a distinct line with regard to energy, or it can be higher energy. And actually, what I usually do is I will kind of draw an invisible line above that line, higher energy, okay, or higher energy, and kind of as I keep putting my hand up, I'm getting more and more energy, okay. Those are all quantized values of energy. So the thing is, there's no in-betweeners. Okay, it's a jump sort of thing. Okay, that's all it means. Quantized value can exist in one of possibly several discrete states, but not between them. No betweeners. Not that there's anything bad about betweeners. So look for a vocabulary section on Unit 2 exam. It's what I've usually done. Let's see what I end up doing. Probably what I usually do. So these two chemists that I'm showing here are both at the same elevation. Okay, but can you see the dude on the stairs, that his elevation is quantized? He can be on this step, or this step, or this step, or he can go down a step. Okay, his elevation is quantized. The dude on the ramp is like not quantized. Okay, so this is more like what electron energy is like. So we can kind of think of, and again, you'll see me put my hand here, and then I'll put my hand up a little bit farther, and I'll put my hand up a little bit farther. What I'm doing is kind of like, you see these rungs, and I'm talking about energy. Higher energy, lower energy. Okay. So already you get the first kind of way that electrons get to kind of be divvied up or broken down. This variable n is called the principal energy level. Okay, or that's what I call it, the main energy level. Okay, so we will be visiting that. N is called I call it the principal energy level. E for energy. Okay. So, because what we're going to see is those principal energy levels actually kind of some of them especially kind of like, if this is the main principal energy level, it kind of splits. So we have what we call subshells coming up. All right. Okay, so here we have, talking about the simplest atom, the hydrogen atom, atomic number 1, so it has 1 proton, and it's kind of cool because you'll see that most isotopes of hydrogen have no neutrons in them. So they basically run around with a proton and if it's neutral, a little electron. Isn't that adorable? Okay, so and I think we talked about this before, let's pick on hydrogen. If an atom is neutral, it has no charge, then the number of protons need to be counteracted by the same number of electrons outside. Okay, that's why hydrogen, 1 proton, 1 electron. It's neutral. Now we're going to see, and some of you already know, actually electrons can be stripped away, and actually electrons can be piled on. The protons have to stay the same. Okay, so so that cute little hydrogen atom, that cute little electron around a hydrogen atom actually can be here at this principal energy level, and n is equal to 2, n is equal to 3, n is equal to 4. Now, when you get beyond hydrogen, when you get an extra electron, then things kind of split up a little bit. So we'll be talking about that. So we are basically going to focus on finding homes for those electrons. It's like one of the things our family likes to do is actually foster kittens. And so we always get excited when the kittens find homes. So we're finding homes for these electrons, okay? But when we find homes for these electrons, we're going to stick them in their lowest energy, okay? Lowest energy possible, and that's called the ground state, okay? The lower the energy of the electrons, I keep kind of doing this, lower the energy electrons, okay, the more stable the situation. And we're going to be focusing on finding homes for electrons in their ground, what we say ground state. Okay, so the opposite of ground state is excited state. So those would be 2 possible terms you might see on your unit exam in a couple weeks. So the thing about excited state, it happens all the time. The funnest thing around the 4th of July, we definitely see electrons doing all the cool fireworks. Okay, that's all about electrons. Because basically what they do, and it's the whole timing thing of fireworks just amazes me, the science of fireworks. Okay, but basically they take, and I'll kind of point to our periodic table, I'll kind of focus on the metals, which most of them are metals, right? We talked about that in this actually that's going to be in your test too, this whole kind of metals and non-metals. Remember, make the invisible jag, or it's not so invisible there, it's yeah, along the metalloids, exactly. And over there in the small kind of triangle is the nonmetals, and all these are metals. So basically what fireworks do is to take certain metals and kind of bundle them up, shoot them up, and basically, like I said, it's a timing thing. And at the right time, basically, they heat the metal, and the electrons around a metal atom get excited. Electrons around a metal atom get excited. When they fall back down, they emit that beautiful color that we see. And basically, we said that it's quantized, so the amount that they fall actually will give a certain wavelength, a certain energy of color. So it's kind of cool. So, all right. So we're going to find homes for electrons. I told you the principal energy level, N, is kind of like the, well, the word principal might give it away. Actually, it's kind of it's the broadest. N is the broadest. Electron orbital is the most specific. Okay. Electron orbital, I think of it as two things. I'm going to go ahead and draw a box. When we start to draw boxes, these are going to be our orbitals. And we are going to put them at various, I'm going to go ahead and draw an energy, let's pick on blue. Okay, this is actually increasing energy as you go up, kind of like we're talking about. So those boxes are called orbitals, and we're actually going to, those are where we're going to put electrons here in a minute. But in the meantime, orbitals are also kind of that spatial thing. On Schrodinger's model where it went, okay, that was an orbital. Kind of the general location where electrons are going to be, and also there's an energy associated with it. Okay, so electrons are found in orbitals. So orbitals is kind of the, I think I'm going to go ahead and start kind of drawing something over here. And we'll kind of build on this as we go. A few slides ago, this is going to be increasing energy. A few slides ago, we had n is equal to 1, n is equal to 2, n is equal to 3, and I might need to kind of have a little more space here. These are principal energy levels. All right. So clear down here, let me go ahead and draw a box. That is my box, and I want to start you get to thinking, what this says is every orbital can hold how many electrons? 2. That's critical, exactly. So we're going to use arrows, and sometimes my arrows have 2 sides like that, and sometimes I get lazy and I just make it one-sided. So there is 1 electron. It can hold 2. Now here's the catch. If we put 2 electrons in there, to show that they're unique, and actually I don't get to this until the very last slide in this part, but to show that they're unique, actually I'm going to go ahead and draw the second arrow down. And that actually, the word for that is actually spin. You have 2 options for spin. You have an up spin or down spin, +1/2 or -1/2. So actually that is showing uniqueness. There, very good. Which element has 2 electrons if it's neutral? Helium, very good. She's got the periodic table memorized, I must warn you. So actually, helium's electrons are generally like this. Very good. All right. Well, orbitals are arranged in what we call subshells. Okay? So let me go ahead and I'm going to kind of give names to these subshells in a minute, but I'm going to bump up to principal energy level n is equal to 2, and I'm going to go ahead and draw 1 orbital here. I don't think I'll put electrons in it, if that's okay with you. And then I'm going to draw a set of orbitals here. Remember, boxes are orbitals. I can put 2 electrons in each box. Okay? This right here, that I have 3 boxes, do they look like they're at the same energy level? Because they are. Those are special orbitals, all at the same energy level. This actually is what we call a subshell. All right? This is a subshell, and this is a subshell, but it's not clear. It's not just very much exciting. These are subshells. Actually, I have 3 subshells. All right. All right, we already talked about the last one, the principal energy levels. That's the N. Okay? So that's the N. Not too bad. Some people really get into these. So let's, while we're at it, just for kicks, let's see, we want to pick on beryllium, the element beryllium. Okay, find it on your periodic table. Beryllium. So what's its atomic number? Yeah, Be, beryllium. Atomic number 4, very good. So it has 4 protons in its nucleus. If it's neutral, how many electrons does it have? It also has 4 electrons. Exactly. So here we go. Is that not adorable or what? That's beryllium. 1, 2, 3, 4.
Oh.
See how that works? Yeah. Okay. Very good. Okay. Degenerate orbitals. It sounds like a bad thing, but actually degenerate orbitals should make you smile. As I've gone up here into n is equal to 2, that second subshell, this is one subshell and n is equal to 2, this is the second subshell and n is equal to 2. Each of these orbitals, the 3 together, are what we call degenerate orbitals. And it's a good thing. They're orbitals that boxes in the same subshell. It's wonderful. Okay, so put another way, a subshell of orbitals, like you see here, okay, has the same energy. If they're in the same subshell. So let's go ahead and see, these are all n is equal to 2. This is n is equal to 1. I'm going to go ahead and go up to n is equal to 3. And maybe you kind of see a pattern here. I'm going to draw one box here. That's one subshell. N is equal to 3 actually has 3 subshells. There's my second subshell with 3 boxes. See the pattern? And my third subshell, and it's all about oddsies. So it's actually going to have 5. Okay? That's n is equal to 3. 3 subshells there. All right. All right, so I already kind of warned you about this. Can you see these are the 3 subshells when n is equal to 3. These are the 2 subshells when n is equal to 2. Here's the 1 subshell when n is equal to 1. Let's go ahead and start putting a letter with these. I'll just do it this way. S. 1s, sp, 2s, 2p. Do you see how that goes? 2s, 1 box, 2p, 3 boxes. 3s, 3p, 3d, and they are lowercase, so that piece are kind of big. But okay, not too bad. And I kind of ran out of room. But if we're sticking with the pattern of oddsies, it went, an S has 1 orbital, a P has 3 orbitals, a D has 5 orbitals, so an F has 7 orbitals, exactly. And that's what we're going to see. Exactly. But like I said, I kind of ran out of room there. Okay. So, 1, 2, 3, and 4. N is equal to 1, 2, 3, and 4. We actually, on the previous slide, did this much. N is equal to 1, 2, 3, and 4. When the principal energy level N is equal to 5, guess what? You have 5 subshells possible. When N is equal to 6, 6 subshells. When N is equal to 7, and actually that's the highest we go, N is equal to 7, you have 7 possible types of subshells. But notice that beyond F, the G, H, and I, that's beyond F. Notice that when we, on Wednesday, start to find homes for electrons, we aren't going to use G, H, and I. Not as we are finding electrons in their ground state. Okay? So actually, they're kind of ghosts out there as far as we're concerned. But they do exist. Okay? This actually, if you want to put remember for later, you can, but I'll remind you for later. I said all electrons are not created equal. If you have 6 electrons around an atom of carbon, then each of those 6 electrons are unique with regard to their 4 quantum numbers. The other way that not all electrons are created equal is there are some special electrons, and they're called valence electrons. Okay, and they are the outermost electrons, not necessarily what we call the last added, but the outermost. You know where your valence electrons are if you look at, I'm doing this, if you look at the period that the element's in. Let's pick on iridium. What's the symbol for iridium? What do you think? IR is the symbol for iridium. What's its atomic number?
77.
77, very good. And what period is it in?
6.
I get 6. Is that what you get 2? Good. It's in period 6. Yeah, exactly. So when we find homes for the 77 electrons around an iridium atom, the valence electrons are going to be in the principal energy level, n is equal to 6. Okay, so that's how that goes. Again, we'll come back to that. All right. Not too bad. So we did this. The 1, 3, 5, and 7. 1, 3, 5, and 7. And I think I'll put this on the board, or I might put it up here. Okay. Corresponds to s-subshell, a p-subshell, a d-subshell, and an f-subshell. It's kind of fun because the S-type subshell only has 1 box. The P-type has 3 boxes. What I started to say, it's kind of fun because all energy levels have S, right? But only when you get to energy level n is equal to 2 do you pick up a P. When n is equal to 3, you pick up a D, a D. And it is lowercase. Like I said, though, my P's seem to be getting kind of large. An F. My boxes get sloppy. I'm working on it. So clear at the end of this this part, you're going to see basically, but I'd like to go ahead and do it here if you don't mind. I'm going to put max electrons, maximum number of electrons. So what's the maximum number of electrons you can fit into an s-subshell? These are all subshells. When you max out with electrons here, how many can you fit? 2. I agree. Very good. How about a p-type subshell? 6. Exactly. Does everybody see that? That's going to help you out for finding homes for electrons. How about a d-type?
10.
10. I'm liking it. And how about an f-type? 14. Exactly. Yep. Okay. So it's not too bad. It's really not. If you're a visual person, it's like, oh, I can see that. Okay. So where we have these principal energy level n's that have more than one subshell, okay, it's going to be like I've drawn it up here, that when n is equal to 3, there are 3 subshells possible, and the 3s is the lowest, followed by the 3p, followed by the 3d for that principal energy level. Pretty good. So let's talk shapes. Again, this is something sometimes I put on my tests because I think it's kind of good you know the orbital shapes. The S's are, and I only focus on S's and P's. So S's have this spherical shape, kind of like the classical in a sphere. But when you get to a P, and I'll show you some pictures here in a minute, when you get to a P orbital, these pair of electrons don't make a sphere. They make basically a dumbbell with the nucleus at the center, kind of a dumbbell. Okay, so where the handle is where the nucleus is, and then it kind of fans out like that. That's where the pair of electrons are for the p-type orbitals. So, S, like an S-type? Yep. So kind of what they've done here is where it looks like there's the greater density of dots, that's where there's a higher probability of finding the electrons. Notice that the probability of finding an electron at the nucleus is 0, as I understand it. Okay, so instead of dots, we could go ahead and kind of put that on the boundary. Calculus is great for handling statistics and distribution, things like this. This actually has both the dot, dot, dot and the boundary. Okay, I have a better picture. I'm not going to animate these, but I have a better picture coming up. The picture that you're looking at, is actually doing these two. Okay, oops, did it go back? Well, maybe I did go this. This right here, the picture you're looking at, is doing these two, where the 1s is this and the 2s is this. So basically, it reminds me of those little Russian dolls that you get where they're little and they get bigger. Okay, so the lower principal energy level actually is closer to the nucleus with the lower energy. Higher energy, farther from the nucleus. Okay, so these are the dumbbell-shaped ones. Like a dumbbell. Now, the cool thing about this, I think this is so exciting. So you guys would agree that there are 3 orbitals, 6 electrons, right? 6 electrons. If you have a subshell, a p-type subshell that's entirely filled, you have 6 electrons, but they kind of go in pairs. So there's one orientation of the double lobes. There's a pair of electrons that do that, a pair of electrons that do this, and a pair of electrons that do this. So basically, at the origin, 0, 0 in all cases, that's where the nucleus is, and the pair of electrons skitter. They go along the x-axis, along the y-axis, and along the z-axis, however you want to say that. Okay, so all together, they look like this. Okay, so that's how the electrons, that 6 electrons that can possibly be in a p-type subshell, that's how they orient themselves. Okay, and each lobe is each pair of lobes is an orbital. I think that is so cool. Okay. So the D-type gets a little more complicated. Okay, but again, D-type subshells have 5 orbitals, so we need to have 5 spatial regions where pairs of electrons hang out associated with each one of those orbitals. So we have this kind of situation, this kind of situation, this kind of situation. Okay, 1, 2, 3, 4, and this one. Is that not weird? That last one. You're like, really?
I like that one.
I know. Okay, so that's
Very sciencey.
the 5 degenerate orbitals of a D-type subshells. So this kind of looks at you see the 1s, 2s, and 3s over there on the board. 1s, 2s, 3s. They just keep getting bigger, but they're all spherical. Okay, only when you get to n is equal to 2 do you pick up the p-type. Okay, so there's 2p and 3p. Just dumbbell-shaped, but the 3p is bigger than the 2p. And then when you get up to n is equal to 3, then you pick up the d-type subshell. There you go. And in case you're wondering, here is a model of the those beads will kind of beat up, but there's a model of the f-type subshell that has 7 orbitals. 14 electrons if you entirely filled the subshell. Okay. So clear back a few slides ago, I said we're going to make boxes or orbitals, and each orbital or each box can only accommodate 2 electrons. So that is known as the Pauli's exclusion principle. Again, sometimes this makes it to my test. I don't know which one will make it to my test. The whole up and down arrow that I said we have to do, if you have 2 electrons there, okay, you visually show it as one pointing up and one pointing down. Actually, that has to do with this last spin number. Okay. Okay. M sub s is spin. And basically, there's 2 options for spin. there is a +1/2, and it goes up, and there is a -1/2, and it goes down. Okay, so pretty good. All right, so this actually is what you told me a little bit ago, that each subshell type is limited to the number of orbitals, and because you can only fit 2 electrons in each orbital, it's limited, its capacity to accommodate electrons is also limited. And again, we're going to revisit this on Wednesday. Okay, so you max out if it's an S-type subshell, 2 electrons, P-type subshell 6, D-type 10, F-type 14. All right, so let's take a look at these. These you don't need to use your calculators for, which is kind of nice. So 19 is list the 4 possible subshells in the quantum mechanical model. So the 4 possible subshells, S, P, D, and F, yep, exactly, maximum number of electrons. So you're cool with that, I'm sure. Can I borrow someone's book for the next, because I'm not on the internet. Thank you, sir.
I don't have that book with me.
So, great.
Well, the book. Yeah, the book.
So for the last ones, they're not too bad either, I don't think. 43 through 46. So, I just ask you questions about that. Okay, 43 says sketch the 1s and 2p, the 1s and 2p orbitals. You think you can just do your best? The s will be spherical and the p will be dumbbell shaped.
Dumbbell thing.
How do the 2s and the 3p orbitals differ from the 1s and the 2p? I think they're larger, they're farther from the nucleus, they're higher energy. I do. The 44 says sketch the 3d orbitals. Just do your best. They'll be 5, right? Just use the book. And how do they differ from how do 4D differ from 3D? 45 is which electron on average is closer to the nucleus, a 2s or a 3s? I think 2s, I do too. 46, which electron is on average further from the nucleus, a 3p or a 4p, further from the nucleus?
4P.
Yeah, so it's, okay, and then on Wednesday, we'll just start finding homes for electrons.
Yay. Electron homes. They'll be so happy.
Be what?
I said they'll be so happy.
They will be so happy.